Okay, let us start. In previous talks, I proved the following implications. So we consider links in S3. So L and L prime. No, how about A and B? Yes, A and B will be links in the 3 sphere. Piecewise linear link. Today all links will be piecewise linear. And I put the following implications. If A and B are topologically isotopic, then A and B are n quasi-isotopic rho n. I think this was called theorem 1. This was in the first talk. And then I proved that if A and B are n quasi-isotopic, then they are not separated by type n invariants. So finite type invariants. Which are well defined up to PL isotopy. Well defined up to PL isotopy means that they are not changed when we insert a local knot into our link. It's equivalent. And this was theorem 2. Which was also proved in the first talk, but then in the second talk I added some details to this proof. And also theorem 2 said a little bit more. Actually theorem 1 also said more. Actually A and B are strongly and quasi-isotopic if they are topologically isotopic for all that. And theorem 2 said that if A and B are n quasi-isotopic, then A and B are not separated by colored finite type invariants, not just usual but also colored. Yes, but today we are not going to use this, so let me not write it even. Okay, now in the end we want to prove that A and B are PL isotopic to links that are not separated by finite type invariants. So here are all finite type invariants, not just those which are well defined up to PL isotopy. But we have PL isotopy here. So there will be some intermediate implications. And to prove this, we need to obtain them, we need the following lemma. A and B are not separated by type N invariance well defined up to PL isotopic if and only if A and B are isotopic, are PL isotopic, to links which are not separated by locally additive. Type and invariance. Now, what is locally additive? So this is almost what we want actually, except that instead of all finite type invariance, we suddenly have this locally additive. But this will complicate our life. So what is locally additive? This means that V of the connected sum of L and K is equal to V of L plus V of K if K is a totally split link. Totally split means that its components are contained in disjoint balls. So each component can be a non-trivial knot but they are contained in disjoint balls.
Ну тогда L totally split.
No, L is not totally split. L can be any link, and this is why I call it locally additive and not just additive.
Но если я один линк заключил как шаг, то автоматически другой дополнение заключается. Нет разве?
So the picture is like this. We can have, for example, the Whitehead link and maybe a third component here, and then I'm taking the connected sum. So my components are numbered. These are 1, 2, 3, and these are also 1, 2, 3.
Две компоненты. Зачем три? Мы АБ считаем. Теория АБ.
No, A and B are links. These are
много компонентов.
Yes, they can have 7 components and 7 components. Same number of components. So I'm taking the connected sum of this knot with this component, of this knot with this component, and of this knot with this component. Actually, it can be any band, it can go around somewhere.
Не, ну тогда, я думал, что когда две компоненты, верно ли, что если две компоненты, L и K связаны, то если K totally split, то L тоже totally split.
No, it's not true. No. Because you can have just Whitehead link and add some local knots on its components, and this will be what is written here. L is the Whitehead link.
Нет, я спрашиваю, если L узел и K узел, у вас не узлы. Ладно, хорошо, понятно.
If K and L are knots, then there is no condition. Then it's just additivity. But for links, it's different. So actually, this connected sum is going to be well defined precisely because of this condition that K is totally split. Because I can choose a different band here. It can go here. Yes, and if this link is non-trivial, then this connected, the result depends on the choice of the band.
Если они в шарах, то все равно.
Yes, but if they are, if it is totally split, then it doesn't matter, because I can move this small knot here along the band until it will become a small knot here. So I'm just tying local knots on the components of my link.
У вас тут 1, 2, 3, 4.
No, one, 2, 3. No, 4.
Ну ладно.
А вы сказали, что если оба узла, то нет условия. Имеется в виду, что любой...
Totally split is not a condition, but additivity is a condition still. So for knots, this word locally would not be needed. It would be just additivity. Local means because of local knots. I'm putting local additivity there. So it is additive when I'm adding local knots to my components. But I want to have an invariant which is...
К у вас в этом примере то, что внутри трех шаров.
Yes. Yes, this is K and this is L.
А компоненты у вас не крашеные. Какие получатся? То есть у К уже очень много компонентов получается.
Нет, но крашеные. Но надо первую с первой, вторую со второй. We join the first one with the first one, the second one with the second one.
Узлы в шариках. Там могут быть две компоненты в шарике?
No, only one in each ball. This means totally split. If it is just split, then there can be several components in one ball. But totally split means that each ball contains just one component.
Yes.
Okay, so the reason why I'm speaking about totally split links and not just local nodes is because my invariant V is an invariant of m component links. So the number m is fixed. V is an invariant of m component links. It is not an invariant of nodes. And so I'm constructing this totally split m component link out of nodes.
Но как же тогда вы считаете V от K, если у вас там... хотя да, у него тоже три компонента.
Yes. So K has the same number of components and this is defined. Everything is defined here, but we don't know, they don't have to be equal. If V is a finite type invariant, they don't need to be equal. Okay, so let's prove this level. Any other questions so far? Okay, proof. So in one direction it should be obvious. If A and B, the direction going up is obvious. If A and B are PL isotopic to links which are not separated by locally additive type n invariants. Well, this, and we want, okay, this we are given this, and we want to show that A and B are not separated by type n invariants which are well defined up to PL isotopy. Well, if they are well defined up to PL isotopy, then they are locally additive. Because when you are adding a local node, the invariant is not changed. So when you are adding a totally split link, you are adding 0.
Наверное, обратная тоже импликация верна. Это инвариантная?
No. This is about the implication going up. Okay?
Что значит going up? Куда? В какую Вот в этот линк.
Вверх, вот этот, this. So, we want to show that A and B are not separated by type n invariants well defined up to PL isotopy. We know that they are PL isotopic to links which are not separated by locally additive type n invariants. Okay.
То, что вы, извините, Сергей Александрович, то, что вы в шары запустили, это же и есть маленькие узлы. Вы их можете PL стянуть, там одна компонента, и поэтому назад тоже получается.
No.
Если у вас есть PL изотопия, у вас в шарах накапливается.
Petr Mikhailovich, let me prove this and then let us discuss the opposite implication.
Покажите, да.
So we want to show that A and B are not separated by type n invariants which are well defined up to PL isotopy. We are given that A and B are PL isotopic to links which are not separated by locally additive type n invariants. So we have this V, this type n invariant which is well defined up to PL isotopy. It is not changed, it is invariant under this PL isotopy, and it assumes equal values on these links which are not separated by locally additive invariants because our V is locally additive. So, okay. So let us call these links A prime and B prime. V of A equals V of A prime because these are PL isotopic. Now this is equal to V of B prime because A prime and B prime are not separated by locally additive type n invariants, and we have our V is locally additive because it is even well defined up to PL isotopy. Now this equals V of B, and this is what we want. A and B are not separated by our invariant V.
Почему B' равно B?
By the same reason they are PL isotopic. Okay? So this is the obvious direction.
Ну ладно, доказали.
Простите, как по-русски будет total split?
Вполне разделенная, но сплит разделенная. Totally полностью, может быть, вполне.
Ну говорят вполне, да.
Наверное,
Правда,
вполне
по-русски, когда говорят вполне, так звучит как-то неубедительно.
Okay, so let's now prove the more interesting direction. Petr Mikhailovich, questions?
Нет, я понял доказательства.
In the opposite now.
Нет, но я такие головоломные доказательства скоро отрублюсь, но пока что я слежу нормально.
Okay, so can I continue with the other direction? Okay, so the other direction I have to write it here. Its direction goes down for the lemma. And now I have to do some construction actually.
Вы одну сторону только доказали.
Yes, now I'm proving in the opposite direction. So let me define A prime as follows. This will be the connected sum of A and KB. What is KB? KB will be the totally split link which consists of those nodes that we have in our link L. So I just take all components of L and put them separately into small balls.
Они же там заузлены как-то.
Yes. So from this picture, so if this is L, then KL will be the following picture. The first one is trivial, the second will be this. Well, in this case it is trivial, but it is occasional. Wait. And the third will be this. And they are contained in in small balls. I just draw all components separately.
Потом вы ленточки вытягиваете, как получится между ними, что
No,
это же не
no.
эквивалентные.
Yes, these are different links. This was link L, and this is a link KL. But it is well defined. This KL is well defined up to ambient isotopy.
Ну, видимо, да.
So I sort of localize all nodes that I had in my link L. And now I'm adding A and KB. And this will be A prime. And B prime will be B to which I am adding KA. So this one is PL isotopic to A, and this one is PL isotopic to B. But also, if you look just at the node types of the components, they are the same. K A prime equals K B prime.
Ну, видимо, да.
Okay. So this is my construction. Now let us prove the lemma using this construction. So I know that A and B are not separated by type n invariants, well defined up to PL isotopic. I want to show that A and B are PL isotopic to links A prime and B prime. These are those links which are not separated by locally additive type n invariants. So it remains to show that A prime and B prime are not separated by locally additive type n invariants. Okay, suppose V is a locally additive type n invariant. So I want to show that V of A prime equals V, so I don't know this, equals V of B prime. But I can write already that V of A prime equals V of A plus V of KB, and this one equals V of B plus V of KA. Now what I know? I know that A and B are not separated by type n invariants. No, I think this is maybe not what I need. I know that A and B are not separated by type n invariants, well defined up to PL isotope. So actually I want to construct an invariant which is well defined up to PL isotope. So let's construct such an invariant. V bar of L is defined by V of L minus V of KL. So V was locally additive, and now I am subtracting this local nodes, its value on this totally split link, and then V bar will be invariant under PL isotopia. Because if I'm adding some other T is totally split. It's the same as making a PL isotopia. To do a PL isotopia is the same as to add local nodes, and to add local nodes is to add a totally split link. And this is the same as v of L connected sum with t minus v of k L connected sum with t. But v is additive, so this is the same as v of L minus v of t plus v of t. And here, of course, this is also the same as v of k L minus v of kt. But kt is the same as t, because t is totally split. So these two terms cancel, and I have v of L minus v of kl, just what I had before adding t. So v bar is invariant under PLS. Okay, now I want to prove the theorem. So I want to prove that v of A prime equals v of B prime. And I have this formula actually, which I can use. So I can write v of A prime equals v bar of A prime minus v plus v of k A prime. And I can do the same for B prime. Okay. Now Ka prime is the same as Kb prime. So these two terms are equal. And what do we have here? Okay, so A prime is PL isotopic to A, and B prime is PL isotopic to B, and V bar is invariant under PL isotopy. So I can write that this equals V of A, and this equals V of B. V bar.
Ну, не совсем, потому что вы приравняли, надо волнистую черту еще добавить. Она одинаковая, но добавить надо.
Yes, you are right. You are right. It's not good to write this, but the difference V of A prime minus V of B prime equals the difference of V bar of A prime minus V bar of B prime, and this equals V bar of A minus V bar of B. Okay? So this is because these two terms are equal, and this is because A prime is PL isotopic to A and B prime is PL isotopic to B. But now V bar is well defined up to PL isotopy, and we are given that A and B are not separated by type n invariants well defined up to PL isotopy. So this is 0. Okay, so V was type n invariant, and then V bar is also type n invariant. You can check it. If you make some self-intersection of a component here, then in this picture you can also make a similar self-intersection. You can just treat this component separately, and all self-intersections you will see here.
Ну ладно, доказали. Ну, хорошо.
Okay, any questions?
Yeah, where did you get Ka equals Kb from?
They are not equal, but this is Ka prime and Kb prime, and these are equal because Ka prime equals Kb prime.
They are primes. Okay. Where do they come from?
So A prime is the connected sum of A and Kb, okay? And B prime is the connected sum of B and Ka. And so when I'm taking this K operation, I'm just looking at separately at the components of the link. But then these two are separately, if you look at separately at the components, they're the same.
Okay, I got it.
So then these two, when we subtract this from this, these two terms cancel, so we just have these two terms. And then, so V bar of A prime minus V bar of B prime. And here we can replace A prime by A and B prime by B, because A prime is PL isotopic to A and B prime is PL isotopic to B, and V bar is an invariant of PL isotopy. And then this difference is zero by the hypothesis of the lambda. Alright? Okay, now I'm ready to state, yes, I should say before proceeding, I should say that here A and B, they were links in S3. Actually it was important that they are in S3 because I couldn't use this construction KL if they are just in some 3 manifold. But there is a version of this lambda for string links. I guess I need to define what a string link is. And it is proved in the same way. But I have to define what is a string link. So we draw a cube. And we fix we have a fixed number of components m, and then we draw m fixed points on the two opposite sides. 5. And then we for each pair of points we draw some string between these points. Oops. Seems let's erase some point. That will be okay. So this is like braid, but a braid is monotonous. And this string link, it doesn't have to be monotonous. So I could draw like this, for instance, and then you cannot make it monotonous. You cannot make it a braid. Yes, so the equivalence relation is ambient isotopy keeping the boundary fixed. So these strings are fixed at their endpoints. And what is good about string links is that you can add them. So they form a monoid. For Islam it doesn't matter. Everything what was said about links holds for string links. So for string links, there is a well-defined connected sum of any two string links. We don't need it, we need only connected sum of this form where k is totally split, but it is also defined. And then the proof is the same for string links. Okay?
Да.
So now, why do I need string links? I need them because of the following theorem. This will be theorem 3. So we had theorem 1, theorem 2, and this is finally theorem 3. It says that if A or and B, so A and B are m component string links, are separated by type n. Always confusing. Yes, by type n invariance. Then they are separated by locally additive type R invariance. For some R, which is a function just of n and n. So this R doesn't depend on the links, on the string links A and B. It depends only on this type n and on the number of components. But unfortunately I cannot put n here. I mean, I don't have an example. Maybe you can prove that you can put n here, but I cannot prove it. And I have some doubt that other people are able to. So maybe, of course, maybe you can say that I cannot prove it because I'm stupid, but I'm not sure if other people would be able to prove it.
Посылка звучит как, если А и Б просто разделяются
Инвариантами порядка n, то тогда они разделяются локально аддитивными инвариантами большего порядка. Какого-то большего порядка, но контролируемого большего.
То есть в стиле предыдущих термин должно звучать как если они неразличимы никакими инвариантами, никакими локально аддитивными инвариантами.
Достаточно высокого порядка, то тогда они неразличимы никакими инвариантами порядка n заданного порядка. So, yes, so...
Это достаточно высокого, вот если формулировать в обратную сторону, можно убрать, что просто, то есть равносильно ли это теорема такому утверждению? Если А и Б неразличимы локально аддитивными инвариантами конечного порядка, то они неразличимы инвариантами
Конечного порядка.
Это следствие. This is corollary. Let me write the contrapositive.
Нет, если к бесконечности перейти, то это тавтология получится. Потому что если R равно бесконечности...
Нет, не тавтология, локально аддитивная.
Если они локально аддитивными не различаются, то и они вообще не различаются.
Okay, so an equivalent statement of the same theorem. So there exists an R, which is a function of n and m, such that if A and B are not separated by locally additive, that are invariants, then they are not separated by type n invariants. So,
Нет, ну сейчас, подождите. R-тип инвариантов локально аддитивные же сильнее, чем если
да,
просто n.
да.
Ну так а в чем тогда смысл? Только что...
Порядок меняется.
Нет, я говорю, что если r равно бесконечности, то теорема становится вырожденной, потому что если какие-то линки не разделяются с дополнительным условием, то они не разделяются.
Нет, это не очевидно. Очевидно в другую сторону. We have, so not all invariants are locally additive. If some links are not separated by locally additive invariants, we don't know if they are separated by all invariants. Maybe there are some non-locally additive invariants which separate them. But yes, actually I should mention here, maybe I can erase this picture. What should I, how about I erase this? I should mention a theorem of Labira and Stanford, I think. I'm not sure if Stanford did it independently or not, but anyhow. So they proved that if nodes K and K prime are so how about this? Nodes K and K prime are separated by additive type n invariants if and only if they are separated by all type n invariants.
Здесь нет функции r.
Yes, here the same n, but only for nodes. Links are more complicated than nodes.
Ну да. В этом узле m равно единице, а единицей можно пренебречь в такой теореме. Понятно.
So actually, my proof of theorem 3 is a modification of Habirov's proof of this theorem.
Но эту функцию вы ее можете описать?
Yes, this function is explicit, but it's
Но она какого порядка?
some factorial, something like.
То есть она очень... Ну ясно.
Quite fast,
Нет,
quite
если
rapid.
факториал, ладно, все ясно.
And the function actually comes from algebra, absolutely. It's a group theory. The function comes from group theory. Okay, now I'm almost ready to complete the proof of, to complete this implications modulo theorem 3. So the problem with theorem 3 is that it is about string links, and I cannot prove such a theorem about links in S3. So I have to somehow pass from links to string links. And I think I have to do it at the previous step. So I think I have to erase this also. And write that A and B are I think here I should write for each n, A and B are closures of n quasi-isotopic string links. And unfortunately I cannot do this step later after I pass to invariance after theorem 2 was applied, because it will be too late to do it.
А вот когда вы квантор ставите любого n в конце, это что означает? Что вы для каждого n можете доказать или сразу для всех?
It means that it has to be here.
Понятно.
Okay, so let's prove this implication. If the two links are n quasi-isotopic, then they are closures of n quasi-isotopic string links.
Короткий вопрос. Разве не любое зацепление это...
Замыкание струны, конечно. Да. Of course, every link is a closure of a string link. But this is, we need a little bit more. We have two different links. We can of course represent them as closures of two string links, but the question is whether these string links will be n quasi-isotopic. And actually, I cannot do it. I cannot do the same closure for all n. So I have to put n here because I will have different closures for different n. Well, one closure, so for A, I can take the same closure for all n. So, n quasi-isotopy consists of some number of crossing changes. And, of course, when I have a link, so my link A can be represented as the closure of a string link. And actually there is a standard way of doing that. Namely, I can draw such arcs well, it's not going to look very beautiful.
Что вы хотите сейчас сделать?
I'm constructing a standard closure of a string link.
Ну, наверное, раз там точки выведены, что бы вам не построить. Ну вот как вы нарисовали, да.
Okay, so there is this operation of standard closure of a string link. And it's a trivial theorem that every link is ambient isotopic to such a picture. Because you just, yes, okay, how to prove it? So if you have some link, like this one, how do you put it into this form?
Ну, это даже я могу доказать.
We will need the proof. Well, first I need to pick some point, some base point, connect it to the components. Let me erase something which is not needed here. Okay, this is our link, and I'm connecting it by arcs to the base point. Every component, for every component, I'm picking some point on this component and connecting it by some arc to my base point. But this is not all. I need to choose a meridional disk here, like this, and like this. And then, and also, I want to put a disk here which contains this triode or an anode, amode. And then I want to attach ribbons to these disks along my arcs. So I'm obtaining a disk which intersects my link in which intersects every component of my link in one point transversely. Now this disk, I can take a regular neighborhood of this disk and it will be a ball, and then this will be the complement of this cube. So the reason why I need these ribbons and disks is because I don't want to get, so for example, if I don't have this disk, I may introduce some twists here and the picture will be the same, but this disk allows me to remember the exact position so that I don't have some twisting here. I don't know if I don't want to have any twisting between these two ends.
Что называется твистинг?
Скручивание.
Как это выглядит?
So the picture of what I don't want to, what I don't want is this.
Ну ведь то, что вы сейчас дорисовали, это происходит внутри куба, а это вроде можно. То есть в чем проблема?
Well, actually it's better to draw. This was a half twist and I want a full twist, I think. So I should draw like this and somehow like this and like this maybe. And this twisted picture is different from the original picture. Well, they are the same link. They are the same link, but they correspond to different string links. Because this disk remembers how, if there was twisting or no, or how many twists there was if there was a twisting.
А можно как-то определить абсолютным образом, есть вот этот твист или нет? То есть сколько раз там?
Ну тут большой произвол, тут не только твист, тут еще ленточки можно по-разному выбирать.
Well, actually, to prove that any link is ambient isotopic to the closure of a string link, I think we don't need these disks probably, but we needed to deal with them quasi-isotopic because I want to I want to draw some picture here which would remember this string link. So if I just draw the ball here, or I draw just this arcs without the ribbons, then I will forget my string link, because a different string link can give me the same picture. Namely, the string link which has this twisting, it will give me the same picture if I don't remember these ribbons. I want to be able to reconstruct my string link from a certain picture here. And the appropriate picture is this.
Сергей Александрович, простите, вот если мы вот на этой картинке... Так. Все, вопросов нет.
Но если вы сделаете лишний твист, то у вас и компоненты в дополнение будет другой стринг-линк. Потому что у вас все это закрутится, я так понимаю, вокруг этой точки. И ничего там хорошего не будет.
Yes, so I want to remember my string link in this picture. I want to be able to reconstruct my string link from something added to this picture, and then I add ribbons, and ribbons allow me to remember my string link. Okay? Without ribbons I will lose it. There will be some different possibilities for a string link. So this is not completely obvious that this remembers this, that you can reconstruct the string link from this picture, but it is a lemma by Levin from his paper of 87, I think.
Почему же не очевидно? Вот вы сказали, что дополнение уже нарисовано, и там точки выведены на дополнение, но вам надо только их расставить, ну уж как-нибудь расставите.
Yes. So we have this ball. We just want to. There is a.
Ну вот они в диске близкие, а вам их надо далеко расставить, но там нет никакого способа запутаться.
So there is a difference between string links and tangles. For tangles, we can move these points along the boundary, and if we just remember this ball here, which is around this n odd, then this ball gives us only a tangle. So these points are not fixed in the boundary. So for instance,
танглом представите, то есть стрингом-лингом представите, вы потом подвинете как хотите.
Yes.
Правда, однозначности не будет.
Yes, but я хочу однозначность. I want it to be well defined. I want to reconstruct the string link from these ribbons. So the problem here is that I move these 2 points along this arc, turn them around each other and move them back. This is how I will get a twisting. And this will give me the same link here if I don't remember the ribbons. But if I remember the ribbons, I cannot do such twisting. It is maybe not completely obvious that this twisting is the only thing that I can do. Maybe you can say that I can permute this point somehow, but Levin proves that no, you cannot do anything else.
Мне кажется, напрямую, покажите просто еще раз, каким образом переставятся точки.
So I move these 2 points along this arc, then move them around each other and then move them back.
Мне кажется, так не получится, потому что, то есть, правильно я понимаю, что вот две стороны вот той поверхности, которую вы нарисовали, соответствуют 2 граням куба с точками, с концами. Вот вы нарисовали набор ленточек с дисками, вот там есть 2 стороны, и они соответствуют граням куба.
Yes, essentially two sides of this disk correspond to these two sides of the cube. Yes, you can see this.
Тогда, насколько я понимаю, вот картинка с твистом от картинки без твиста отличается, ну, то есть если зацепление у них расположить одинаково, то будет перекрут ленточки, а это соответствует тому, что вот у куба грани вот кажется вот так.
Yes, if I remember the ribbon, then I cannot do the twisting. You're right.
Просто непонятно, как вот это вообще реализовать так, чтобы не пересеклись грани куба.
Они упорядочены. Первый, второй, вот 2 точки, ну и выведите их туда.
I can draw the string link in a different way. I can draw it like this. I can choose these points not on the opposite sides, but I can choose them on the same side in the bottom, in 2 rows. And then the string link can be like this, and so on. Now I can do the twisting here. So if I introduce some twists like this. It is half twist, so I have to do another one. Okay, so when I close it up, then this twisting disappears. The closed link will be the same no matter how many twists I insert here. But if I remember this ribbon, then I cannot do this twisting. This ribbon allows me to count the number of twists.
Okay. С твистами стринг-линк могут быть разные. А если вы как обычные, потому что они из одной картинки приходят, они там одинаковые. Но вот теперь вы говорите, что можно аккуратно это сделать и ничего там не подкрутится. Ну, мы согласны.
Okay, so if I draw the ribbons, then I remember the string link. Okay?
Да, да.
Can I continue? So now I want to prove that A and B are n quasi-isotopic, then there are closures of, for all n there are closures of n quasi-isotopic string links. I can fix n. Yes, if they are n quasi-isotopic, then there are closures of n quasi-isotopic string links. So I represent my link A as the closure of a string link. Or equivalently, I draw this picture. So this was my link A, and I draw some ribbons like this and disks. Then I have some n quasi-isotopy applied to A. Some crossing changes like this in this picture with this orange link. So for example, this crossing can be changed into this or something. So I have some crossing changed. Now the only the only important remark that I can do this crossing change so that it doesn't intersect the ribbons, because the ribbons are in the neighborhood of one-dimensional graph, and this graph can be pushed away from such crossings, from such double points, and that's all. So I can keep this picture no matter how many crossing changes I do. I just keep these ribbons in the complement. They move isotopically in the complement, and so in the end I again obtain such a picture. But this picture now gives me a string link whose closure is B. So I prove this implication. So I had an n quasi-isotopy from A to B.
Сейчас вот в квазиизотопе там же, я, наверное, пропустил, что сказали.
У вас вот эти вот ленточки могут в квазиизотопию запутаться, нет?
Вот как раз не могут, потому что они в окрестности одномерного графа, n quasi-isotopy consists of crossing changes, and this one-dimensional graph doesn't have to intersect these small balls which contain the crossing changes.
Кроме кроссинг, там они могут двигаться, но это не важно.
I move these ribbons any way I like. I'm free to move them anywhere I want. So I move them away from such small balls.
Не, ну убедительно. И что, все доказано?
Yes, this implication is proved.
Сергей Александрович, чтобы определить квазиизотопию, нужно определять вот в момент каждого пересечения вот те шары.
Yes, the definition of n quasi-isotopy is complicated. But here I don't need that definition, I just need that it is, I make any crossing changes.
То есть вот в конечном утверждении содержит квазиизотоп.
Okay, you're right. So I had my balls, and now I should, or actually polyhedra, and now I should be able to. So they should be disjoint from these ribbons.
Ну это уже да.
You're right. they must be disjoint from these ribbons.
Ну понятно. Всегда ведь, то есть у нас там на последнем шаге даже будет просто дуга, то есть, которая, значит, которая содержит пересечение последнего шара с компонентой. И нужно просто пересечение с лентой взять с пределами этой дуги на каждой компоненте.
Не, ну там поскольку шары, там надо, чтобы они с лентами не пересекались. Я думаю, это можно сделать. Но там шары накапливаются, и ленты не должны в них заходить. Если вдруг лента заходит, ее надо оттуда вытащить. Ну, это, по-моему, из шара
Проблема в том, что не шары, а многогранники.
Нет, ну, многогранники труднее ленту вытащить.
Плед, даже если шары, и это некоторая проблема, которую я, кажется, не заметил, простите.
Ну да, там, это же шар, он еще плинку приклеит. Там может что, когда будем вытаскивать, может что там действительно что-то запутается. Не, ну, раз выше заметил, то уже нужно считать, что он это самое вклад внес в программу. Но я думаю, что сейчас...
не напрасно.
Я думаю, что сейчас действительно, в следующий раз вы это нам расскажете, ну,
Well, it looks like it's probably possible to do some. Yes, so the problem is that indeed I want to have an n quasi-isotopy of the string link, which means that all these constructions, these balls or polyhedra, must be inside this cube. And here I have them inside S3, and to have them inside the cube, I need them to be disjoint from the ribbons. This looks like almost obvious, but not completely obvious that it is possible to do it. So maybe I'll think about it and tell you later, but right now I...
Нет, ну мне кажется, что если там шар возникнет, который пересекает ленту, то вам надо ленту удалять. Но это действительно некоторая проблема, потому что в шар там ус заходит. Но поскольку вы эти усы все видите, то, наверное, можно удалить ленту из шара. Но
ленту заранее можно до того, как шар появился. То есть с тем, что внутри шара никакой
проблемы
не
ну, может заранее, но во всяком случае что-то делать надо, да.
Yes, something has to be done here. I hope that it can be done, but it is not done yet. I'm sorry. So let's prove everything modulo this question mark.
Потом окажется, что это решает проблему Васильева и заодно и все остальные. Нет, ну верим, что это самое, что нужно пропустить.
Okay, so this is a question mark. I can tell you the other implications. This looked like the most easy implication, but now it's okay. Suppose that this can be proved somehow. Then I think then I'm applying theorem 2. And I get that for all n, A and B are closures of string links which are not separated by type n invariance well defined up to PL isotopy. So this is the string link version of theorem 2. But again, it is proved in the same way. We just do everything inside of this cube, and the argument is completely the same as it was
Но
before.
вы доказали уже теорему 2. я
Yes,
забыл.
yes. Now I need the string link version of
Но
theorem.
вы сказали, что это переносится.
Yes.
Мгм. Просто уже теорему 2 не помните, поэтому ее надо вспоминать. Ну там
Yes.
все было понятно.
Maybe you can believe it. It actually works for any tangle in any three-dimensional manifold. Okay, so we obtain that for every n, A and B are closures of string links which are not separated by type n invariants well defined up to PL isotopy. Now we can apply this lemma. If they are not separated by type n invariants, if string link version of this lemma, if string links are not separated by type n invariants well defined up to PL isotopy, then they are PL isotopic to links which are not separated by locally additive type n invariants. And actually I want these specific links A prime and B prime, so B prime was B connected sum with Ka. So here, let me write it here. So A prime is A connected sum with, maybe I just write it here. So A for every n, A connected sum with Kb and B connected sum with Ka are closures of string links which are not separated by locally additive type n invariants. So I'm applying the version of lemma for string links. So actually I should make this construction A connected sum with Kb and B connected sum with Ka. I should make it for string links. But then I'm taking the closures, and actually you can easily see that the result is the same construction. So I can write it here. Okay, so this was lemma. String link version. Next I'm going to use theorem 3. This was too much of light here. Okay, next I'm going to use theorem 3. And I get that for all n, A connected sum with Kb and B connected sum with Ka are closures of string links which are not separated by type n invariants. Locally additive is omitted because I have the quantifier for all n. In this theorem 3 I have a function, instead of n I have r, but here is for all n, so it doesn't matter. Okay. Now I just have two trivial implications, and here I can just write that A connected some with KB and B connected some with KA are closures of are not separated by type and environments. So why is this arrow true? Suppose we have a type n invariant of links. Then it gives me a type n invariant of string links.
Ну, казалось бы, наоборот, или нет?
Именно так. We type n invariant of links. So I'm going to define double we bar.
Мы тогда должны замкнуть стринг.
Yes. Type n invariant of string links. And I define it as follows. V bar of lambda equals V of lambda bar, where lambda bar is the closure. And you can check that if V was a type n invariant, then V bar is a type n invariant. Because if you make some self-intersections with lambda, then you will have the same sort of self-intersections here. Alright. Alright.
Да, мы поняли.
So we get this arrow. We have two links which are closures of string links which are not separated by type n invariants. Then these links themselves are not separated by type n invariants. I have to add for all n.
В каком месте здесь вообще понадобились струнные зацепления? То есть разве нельзя было без них сразу?
We need string links because of theorem 3. Because I cannot prove theorem 3 for links. I can only prove it for string links. And it's not, I don't think it's because I don't know something, or maybe of course I don't know something, but also it seems that other people don't know it. Alright, so the last arrow says that and so we have two specific links which are not separated by type n invariants. And these two specific links are A connected some with KB and B connected some with KA. The first one is PL isotopic to A because KB is totally split link. And second is PL isotopic to B. And this is what we have here. A and B are PL isotopic to links that are not separated by finite type invariants. So the reason why I want to write these specific links here is because of this implication. I have for all n here, but these links are fixed. And I do want to have these links fixed, not dependent on n. But they are fixed indeed. And they are PL isotopic to A and B. And so I have this implication. Alright? Okay?
Ну, получается, то есть вот аналог теоремы T3 для обычного зацепления не верен, да?
I don't know this. Maybe it is true, but if it is true, it must be much more difficult.
Ну что, вы все доказали, только теорему 3 не доказали?
Yes, I proved everything modulus theorem 3. If you agree, then we can continue to the proof of theorem 3. Okay? No questions? Well, maybe I can make, before moving to theorem 3, one more comment about these implications. I can add here one more implication, namely A and B are PL isotopic. Then they are topologically isotopic, and then I have these implications. So if you look, well, of course this question mark is here, but if you forget about it, if you look from top to bottom, then you get, well, this is a true implication if you believe in the question mark, but the opposite implication from bottom to top is precisely the conjecture that, well, okay, if you forget about this PL isotopy, it is a conjecture so that if two links are not separated by finite type invariants, then they are equivalent. And this PL isotopy is really the same as the Vasiliev conjecture about knots, that finite type invariants of knots separate knots. So I think I should write it. So there are the following conjectures. K will be Vasiliev conjecture about knots. Finite type invariants of knots separate knots. And there is the similar conjecture about links. Finite type invariants of links separate links. Usual finite type invariants, no PL isotopy, no anything. Usual. And this is equivalent to the following. K and one more conjecture C, a conjecture of Habiger and Melikhov. I will say in a moment what is C. And also A1, A2, A3, and A4, where A1 is this, A2 is this, I think A3 is this.
Хаббигер работал с квазиизотопией?
No. I will say in a moment. This is A2. Habiger is here, C.
А3. Ну вы же подписали А2, N квазиизотопия, а там подписан. Зачем вы А2 туда вписали?
Habiger is not about this.
А это зачем вы туда вписали? Это вы, вы декоратор, я понял. То есть если вы туда впишете, тогда значит вот так.
Habiger and Melikhov are about conjecture C.
А вы не написали, что
Yes, I will say in a moment what it is. So A1, A2, A3, a little confused. Yes, okay, maybe enough, A3. You can split A3 into two parts, because here you have all type N invariants, but you can write also about colored type N invariants, and there is a question if they contain the same information or more information, and this and then A3 splits into two parts. But okay, so what is C? Conjecture C is about inverting these two arrows essentially. But more precisely, it says the following. C.
Сергей Александрович, простите, а вы говорите, что такое L?
L is the conjecture that finite type invariants of links separate links. And this says that finite type invariants of nodes separate nodes. So what is C? If two links in S3 are not separated by finite type invariants, they can be represented for each n as closures of string links that are not separated by type n invariants. So it's about finite type invariants of links versus finite type invariants of string links. Do finite type invariants of string links contain more information than finite type invariants of links? Maybe I don't write it.
А гипотеза состоит в том, что нет, не содержит.
Yes, the conjecture is that the same. Well, actually, they had a problem. They didn't say conjecture, they said problem. You want me to write it? No? So, the reason, well, of course, this is now, I should put a question mark here because of this question mark. But,
Sergey, please write it.
okay.
Please write it.
If two links in S3 are separated by finite type invariants, then for each n they are closures of string links that are not separated.
Are separated или are not separated? Первой строчки.
Not separated, thank you. That are not separated by type n invariants.
Of string link.
Of string links, yes. Actually, they write this conjecture not very clearly. So there is another way to making precise what they write. Namely, this quantifier can be put here. So the question is the closure the same for all n, or the closures can be different for different n? This is not clear from what they write, but one of these possibilities is their conjecture. They consider some examples, so they have a whole paper which is devoted to this conjecture, but they cannot solve it.
А гипотеза Васильева для узлов где будет?
This K. So why this is equivalent if you believe this question mark? Well, so
Ну, в вашей теории как-то вообще для узлов. У вас все по модулю P изотопии. Зачем это писать?
Yes. So this is why we have K here separately. Because of assuming K, we can replace PL isotopy by ambient isotopy. There is the following lemma of Rolson. If you have two links which are PL isotopic, but their components have the same knot types, then they are ambient isotopic.
Повторите, пожалуйста.
Let me write it.
Наверное, картинка струнного зацепления не нужна уже.
Ну, по модулю вот этой гипотезы, то есть теорема Ронсона, да, можно туда вписать, будет красивее. Массиве там легче.
Lemma Rolson. If two links are PL isotopic, yes, I should write AB are PL isotopic, and KA equals KB, then when the A equals B, this means ambient isotopy. They are equal up to ambient isotopy. Okay? So I have a different proof of this lemma, which is based on Hashizumi's theorem. About uniqueness of the composition of link into prime links. Actually, not non-split link. If you have a non-split link, then it has a unique decomposition into prime links, but not with respect to this connected sum, which we are interested in, but with respect to a connected sum when you have two links. So this is one link, and then you have another link, and you take just one component from this link and just one component from this link and connect them by a band. Not the first component with the first, the second with the second, no. Just one from this and one from this.
И что?
This is Hashizumi connected sum. And Hashizumi proved that with respect to this operation...
Мог бы вообще не соединять, просто бросить один с другим. Тоже был бы канал.
Yes, but he did this. He did one band. And he proved that with respect to this operation, there is a unique decomposition of links into prime links. So this includes prime nodes, because this can be node, for example, and this will be local node. But also, prime links. Every non-split link admits a unique decomposition into prime links.
А вот компоненты нумерованные, да, у него? Первую с первой, да, соединять? Или какую с какой, ему все равно?
Как Бог на душу положит.
Ну, что-то какая-то сложная теорема, ладно. Может он...
Yes, it's complicated theorem, but it is classical theorem, 1958.
Ну, хорошо, ладно, раз классическая, значит.
So, because of Hashizumi's theorem, it is possible to, if you have any link, it is possible to say, to tell a global part of this link and the local part of this link. Local part consists of all local nodes, and global part consists of whatever remains. Maybe it is not obvious that this is a well-defined notion, but Hashizumi's theorem tells that it is.
Я не понимаю, почему.
У всякого зацепления можно найти локальную часть и глобальную.
Ну, как это связано с... Теорема Хашизуми говорит, что если я взял два зацепления, то я связал какие-то две компоненты ленточкой, и что?
Yes, but one of these two links can be a node.
Ну, может.
And then this Kashizumi connected sum will be just addition of a local node.
Ну да.
So some of the prime summoneds in my link will be local nodes, prime local nodes, and the other prime summons will have several components. So I can just move them to two sides. To one side I move all prime nodes, and to the other side I move all prime links which are not nodes. And this will be the global part, and this will be the local
Ну,
part.
prime links, как вы сделаете? У вас Хашизуми доказал, что есть примарные зацепления, да? В чем теорема его состоит?
Да,
Про то, как вы...
единственность разложения на простые сомножители.
Вот единственное сложение на простые сомножители в классе зацеплений.
Да.
Но если у него это самая связанная сумма такая странная, то уже не единственная. Я не понимаю.
Нет, связанная сумма не единственная, а разложение единственное.
Ну, тогда вообще не нужно связанную сумму брать. Есть единственное разложение линков на простые, так что можно понять?
Yes, if you have a link, there is a unique way to decompose it into primes with respect to this connected sum.
Ну как, если я возьму зацепление и начну разлагать в виде связанной суммы, то ведь я могу по-разному компоненты соединять. То есть, с одной, если я как-то неудачно соединю компоненты, то уже не получится, что ли? Он уже подсказывает, как нужно соединять компоненты, чтобы было разложение. Ну ладно, раз это сложная теорема, может, не надо ее сейчас обсуждать. Мне не так, что она нужна, честно говоря.
Let me
уважу дискуссию.
Let me draw some picture. So maybe two whitehead links. The whitehead link is okay. How about this? You will like this picture. So this link is not prime because I can draw this ball. And it intersects the link in 2 points. So this is a Hashizumi connected sum. But it is so it is Hashizumi connected sum of 2 Hopf links. So this is Hashizumi connected sum, not the usual connected sum. But each of this is prime. So this is how his theorem works. You always have a unique decomposition into prime links.
Но если я посложнее напишу, я же могу по-другому сделать декомпозицию.
And he proved that it is not possible, that there is only one way.
То есть, если я сделаю по-другому, то в конце все равно сойдется. Потом буду еще делать, и я там сделаю, а потом все равно вот это вот должен буду вспомнить.
Yes. It is interesting theorem, I think. The proof is quite long. Maybe just 10 or 15 pages. Many pictures. So if you believe Hashizumi's theorem, then every link has a local part and a global part. And then this Rollson's lemma is more or less obvious, because if two links are PL isotopic, then under this PL isotopy only the local part can change. But also you assume that the node types are the same, so then also the local parts must be the same, and the global parts are the same.
Робсон именно так доказал или по-другому?
No, I think Rollson had a different proof, but I looked at his paper about 25 years ago, so I don't remember exactly.
Лемма Робсона понятно, вот он делает перизотопию, там шары возникают.
Yes, I think
просто до конца, и в конце они возникают как эти вот.
Yes, I think Rollson has a different proof, not using Hashizumi. So anyway, if we have Rollson's lemma, then this PL isotopy which you have in the top and in the bottom is more or less the same. You can forget about it if you believe Vasiliev's conjecture. So if you have, for example, finite type invariants, if you have two links which are not separated by finite type invariants, then in particular the first component has the first component of the first link has the same finite type invariant as the first component of the second link. So then if we believe Vasiliev's conjecture, this must be the same nodes.
А это простое утверждение, что если у зацепления одинаковый вариант, то и у компонента.
Yes, this is obvious.
Ну, если я все зачеркну, оставлю только...
Because if you have some crossing changes on the link, then you just forget about all components except for the first component, and you have the same type of crossing changes on the first component. If you just recall the definition of finite type invariance, you will see that it is obvious. But let me not do it.
Ну просто там для линков там дополнительная информация, она же не стирается для узлов. С чего вдруг мы что-то потеряем, если будем конечные варианты для зацеплений рассматривать? Но ничего мы не потеряем, просто более сложная задача, вот и все. Или вы нет, спрашиваете?
Чтобы говорить, я спрашиваю это, чтобы говорить о том, что информация не потерялась, мы же видим как-то по инварианту узлов построить инвариант зацепления, у которых эти узлы первые компоненты. Я не понимаю.
Ну да, это сложно, но наоборот можно. Ну нет, простите.
Если у вас есть два зацепления, которые не различаются инвариантами порядка n, тогда узлы, которые там первая компонента, тоже не могут различаться. Потому что уж если узлы различаются, то вы зацепления различили. И на таком уровне, по-моему, рассуждения идут. Что там надо достраивать, я не понял.
Yes, if you have an invariant of nodes, a type n invariant of nodes, it always gives you a type n invariant of links. Namely, you just ignore all other components, no matter how they intersect, and no matter how they intersect the first component, this invariant will just not change. Okay? Okay, so what I want to...
Может так всегда такой инвариант. Если есть инвариант линка, можно вытащить инвариант узла, потому что мало ли как он себя захочет проявить, ну хрен с ним, пусть он там изменяется, как ему надо. А это самое, инвариант линка, он все равно помнится. Вот вы сечете, чему равен. Ну вообще да, я тоже уже запутался. Если
мы с Мишей распутались.
Молодцы,
да? Okay, so do you want me to say anything else about this equivalence, or it's more or less okay? I mean, first of all, we have this question mark. Sorry. Also, I didn't prove this because to invert these two arrows and to prove that this is more or less the same, that this is the same as C in the presence of K, it is some work. So it is not completely obvious, but I think more or less the idea of proof is clear from this diagram. Alright? So can I erase this diagram? Yes?
Нет, ну вы просто можете, если есть инвариант линка, вы просто можете подстроить в разность туда, разность инвариантов, который там он подскакивает. Вы туда можете ее вписать, останется инвариант конечного типа, но он уже будет только различать, когда одна компонента, первая пересекается. Вы всегда можете инвариант сложный линка загнать в инвариант узла. В этом, по-моему, проблема, потому что ну, он там сложно как-то перестраивается, но вы это можете проигнорировать. Ну, поэтому, если есть инвариант порядка n для узла, который там что-то различает, то
Okay, so theorem 3 is going to be proved by means of Clasper calculus. Of Habira and Gusarov. They independently invented the same calculus and obtained more or less the same results. So,
А как по-русски класпер?
а так и будет Clasper.
То есть это слово, оно синтетическое?
Да.
Вот Каспер не будет Каспер. Класпер будет Класпер.
So, I want to define a CK move on links or string links. So C1 move is this. Your favorite move. So how to define a CK move? To define a CK move, I need to draw the following picture. So, assuming that a CK minus 1 move is defined, I take some strand in this move, for example this one, and I replace this strand by this picture in both pictures. So C2 move will be the following.
А дальше что заменим?
You can choose now any of these three strands, this, or this, and replace them by this picture. So, one. So I should.
Все три можно, да?
Yes, I should write S is remove. The S is to move, S is remove. For example, I do this one.
Вот второе движение я знаю, это называется дельта движения Мураками-Матвеева. Вот третье движение уже я не знаю, но это да, полезное. А вот сбалансированное движение, второе, это сколько ж надо рисовать картины? Это когда в двух шарах антиподальные вот такие штуки возникают, значит нужно... Или она вообще не входит?
Но сбалансированная это немного другая теория.
Нет, но она входит как частный случай, вот эти цены движения?
Не уверен, скорее нет. Думаю, что нет. Но каким-то образом все эти... Есть какая-то теорема насчет того, что все эти сбалансированные до некоторой степени сводятся к обычным.
Нет, может они формально сводятся, просто надо этих самых побольше струн там собачить. Они сбалансированы, вот так их ищешь, А потом в каждой картинке
Нет,
изменяется.
Петр Михайлович, я вам сейчас не скажу эту теорему, я вам могу ссылку послать.
Ну ладно, не скажете, значит не скажете.
Yes, so like Petr Mikhailovich said, this C2 move is also called the delta move. So it has a different picture. Like this? No, not like this.
Ну, еще нормально. Она показывается.
I think. Should be off.
Не, ну вы сделаете такие же проходы и переходы, да, вот так вот.
Вот я и пытаюсь.
Ну, так
No,
хорошо.
correct, yes?
Правильно, правильно.
Okay. So this is like the third Rademacher move, but not exactly. It's
Что вы нарисовали?
so if you continue this, it continues similarly.
В смысле, вот я просил, какая роль этой картинки в рассказе.
C2.
This is the same as
движение,
C2 move.
то же самое, что
And this picture is symmetric. So actually this tells you that essentially there is just one C2 move.
Ну да.
And for C3 move, well, you can encode these moves by by trees, by unitary valent trees. So C2 move is encoded by this picture, and C3 move can be encoded by this picture. But also, well, here you can draw different graphs. For example, you can draw this, and you can draw also this. So they are symmetric if you allow to permute the endpoints, but not symmetric if you keep the endpoints fixed. Here you can select one of three strands, this or this. So there are three options, and these are precisely these three options.
Правильно я понимаю, что вот та маленькая во всех трех нижних лежит? Ну,
Сейчас не понял.
Вот эта вот маленькая картинка,
Это?
C2. Нет, вот вы граф рисовали, вот это. Маленький граф. Вот справа картинки. Самый
Вот это?
Да. Правильно я понимаю, что он лежит во всех трех нижних?
Ну, конечно, вы его можете вот так вот вложить, скажем. Вы это имеете в виду?
Просто, если вы имеете в виду, что вот эти вот графы, они одинаковые, если их поворачивать, но вот разные, вот так, как вы их нарисовали, то вот это, ну, я пока не понял, как граф строится, но вот именно вот в таком расположении верхней, вот, например, в том графе, в котором вы пытались нарисовать, нет, вы с поворотом нарисовали, а если можно поворачивать, то вот там два нарисованных графа совпадают.
Не нужно поворачивать. Зачем? Когда поворачиваешь, там компоненты все перенумеровываются.
Так вот, если нельзя поворачивать, то вот не повернутая вот эта штука не лежит, вот, ну вот, например, вот в этом вот графе.
Не, ну да лежит она, ну подумаешь, не повернутая.
Well, from this picture,
Сам вперед, можно?
how to proceed from this picture? So here you have to select one of the three strands. In this picture, this corresponds to the three leaves. And then if you, for example, select this leaf, then you draw it like this. Instead of that leaf, you insert a new triolet. Or if you, so okay, this corresponds to this. If corresponding to this leaf, you have this picture, yes, and corresponding to this leaf, you have this picture.
А порядок, получается, не важен добавление вершин, то есть.
Well, if you now, so there is 1, 2, 3, 4, and here 1, 2, 3, 4.
Вот теперь, вот тут граф с самопересечением куда-то делся. Тут у вас 3 графа без самопересечения, там у вас был граф с самопересечением.
Okay. How about just these 3 pictures and
Ну вот эти понятно, да.
Сейчас вопрос будет.
so if you have more more strands, then you can draw also pictures like this. So this is 6 leaves, but I can also draw 1, 2, 3, 4, 5, 6, and these are not equivalent in any sense. Yes.
Можно свою картинку спросить? Вот, правильно я понимаю, что если начинать вот с этого и начинать вот с этого, то получится одно и то же?
I think
Или это
yes.
можно отличать?
I think yes.
Ну там нужно это самое условиться, что начинаем с низшего номера.
No.
Будет однозначно.
If you do it in different order, you can obtain the same picture. For example, here for C2 move, you actually have 2 pictures. You could select this one like we did, but also you could select this one. But
И получается, с сохранением нумерации они одинаковые?
yes, because it is really a symmetric move. C2 move is symmetric. Okay, so there is the following theorem or maybe proposition because it is not so complicated. Okay, theorem. Okay, Khabira, Gusadov. If 2 links or string links are related by Cn moves, then they are not separated by type here Cn, let me write Cn plus 1 moves. Then they are not separated by type n1. Let me prove it for n equals 0, 1 and partially for n equals 3. For n equals 0, an invariant of type 0 will be the same under crossing changes, well, there are no, well, it's a constant, so it doesn't change. What does it say? If two links are related by, any two links are related by such moves, and then type 0 invariants are constants. Nothing to prove really.
Ну, для типа 2 надо развязать вот эти две этих самых штучки.
Yes. Let's prove that type 1 invariants don't change under C2 moves, or equivalent under delta moves. How to prove this? Let me erase this. And let me do the following. Also, this. So I want to draw it like this. And then I want to draw it like this. And then I come here. So here I make one crossing change. Let me draw it in more detail. And here I make one crossing change. Yes. So when I want to move from here to here, I do two crossing changes. But these two crossing changes are very similar, and they can be connected by just making these two intersections. But this will be a second double point, and I have a type 1 invariant. So any type 1 invariant takes the same values on these two singular links. So a type 1 invariant doesn't change under such crossing change, under C2 move. Because its jump here is the same as its jump here, but with the opposite sign. The sign is opposite because we are moving in the opposite direction with respect to the orientations. Okay?
Я не понял. Вы что-то там не договорили. У вас только две точки, у вас есть путь с двумя точками самопересечения. А инвариант, он не знает, что это за путь. Он просто знает, что если есть две точки самопересечения и 4 состояния, то нужно взять сумму 4 инвариантов и приравнять к нулю.
Now, how about this? I want to prove that my invariant of this equals my invariant of this. So I consider this path. The difference between these two invariants is the sum of this and this. But I claim that any type 1 invariant assumes the same values, actually difference between, because here we move in the opposite direction, so okay, I can write plus here but minus here because it goes in the opposite direction, and so this will be with negative sign. But I claim that we assume the same values on this singular link and this singular link, because V is a type 1 invariant, and I can bring this picture into this picture by making additional crossing changes.
Ну где вы его сделаете? Рисуйте. Нет, да прямо на этой картинке. Вот
Here and here.
здесь. Так это две уже.
Yes, but
Уже 3 получится.
yes.
Надо
First this one, and then this one. Each of them doesn't affect because I have type 1 invariant.
Сначала одну, потом вторую.
Yes.
Если вы сделаете одну, то у вас не должен подскочить.
Yes.
Но тогда вы еще сделаете вторую и перейдете в ту картинку. Ну ладно, вроде правильно.
So v of this equals 0 because v is a type 1 invariant and we have two double points.
Ну там уже разность списана туда, а вы берете еще вторую разность. Значит, вы берете разность разностей. Ну, наверное, да.
And it's possible to prove that any type 2 invariant doesn't change under this move in the same way. Do you want me to do it? Okay, let me do it. So,
Простите, вы имеете в виду, что этот ряд продолжится, или это просто примеры, а общее доказательство какие-то?
no, I will not give you a general proof, but I think
Это
it's
упражнение.
not difficult.
Сейчас еще одна теорема, а потом остальное упражнение.
Yes, one more case.
Но вот остальное, оно там все усложняется, или можно, ну, или вот это...
Это зависит от того,
доказательство...
как C3 пройдет. Сильно оно усложнится по сравнению с C2. Давайте C3 узнаем. Если оно не сильно усложнится, то дальше тоже не сильно. А если сильно, тогда придется требовать...
Okay, can I erase this? Yes? Can I erase? Okay? Andres, can you erase?
Yeah.
Uh-huh. So, I split this into the following okay. Now that's this. So here I have singular links. Okay, so the difference of the value of my invariant on these two given links equals, yes, so I can write v of this minus v of this equals v of this minus v of this. Well, it should be plus, but again minus here because I'm passing it in the opposite direction. So now I want to compare these two pictures. So this picture becomes this. And from this, I have to return back to this one. So I'm making a crossing change here, and to draw it in more detail, I should draw this crossing change. And also here I can draw the crossing change. So the difference, I'm interested now in the difference of the values of my invariant on these two singular links. And there is a path between these two singular links. There are two jumps on this singular link with two double points and on this singular link with two double points. And again, I'm passing them in opposite directions. So this difference equals the difference of this and this. But I claim that my invariant of type 2 assumes the same values on this picture and this picture, because I again make 4 crossing changes, and this will be the third double point. And for the third double point, any type 2 invariant doesn't jump. So we proved that any type 2 invariant doesn't change under this remove. Okay?
Значит, вот эту разность надо отсечь.
Yes, so I want to prove that my or I want to calculate the difference of this and this. So I pass between them by the following pass. This green returns here. First I make this crossing change, this crossing change, and I obtain this picture, then it can be redrawn like this, and then I make this crossing change again and return to this. So this difference equals the difference of my invariant on these two singular links with two double points. Yes, because I can make 4 crossing changes and there will be no jump because I have type 2 invariant.
Мне кажется, что дальше будет аналогично.
Well, I think it's not completely the same, because if you take a difference, this remove, it will be not exactly the same. But it's not difficult. It's not difficult. It's an exercise. Anyway, they have this theorem, but it's an easy theorem. The question is about the converse. This is difficult. So
тоже верно обратно.
It's a long story. So for nodes, there is a converse. So, well, I don't know. There are many theorems for nodes. We have the converse. So if two nodes are not separated by type and invariants, then they are related by Cn+1 moves. And this is also a theorem of Habira and Gusar.
Еще раз, если узлы не различаются инвариантами порядка n.
For nodes we have if and only if. This if can be replaced by if and only if for nodes.
Нет, вы написали are-related, это значит связанное. И не сепарированы. Значит, если они не сепарированы,
то связаны.
Ну ладно, хорошо. И это что сделал? Это Это что? Это теорема, да?
Yes, theorem. Okay, how about this? Let us call this Cn equivalent. Cn equivalent. Related by Cn plus 1 equivalent. Related by Cn plus 1 moves. And this not separated by type n invariant, not separated. Let us call just n equivalent. So for nodes, n equivalent is the same as Cn plus 1 equivalent. Yes, and this is also a theorem of Habira and Gusarov. So for string links, for links, so we have one direction, yes, this direction is true, but this direction is not true. And there are different, so Habira has 3 examples for 3 components and more. And Gusarov has an example for 2 components. They have different examples for this. So Habira uses triple mu invariant, and Gusarov uses ARF invariant of nodes, which he evaluates on links somehow by connected sum.
А можно ли быстро сформулировать, в чем там непосредственно важно про узлы, то что они узлы, а то как-то странно тут.
Ну, сейчас еще,
Давайте я чуть попозже.
еще можно спросить, но это самое для линков, опять-таки, с функцией r там получается, нужно правильно сказать, как n и n плюс 1 связаны, и тогда получится отпустить.
Нет такой теоремы.
Ну, должна быть.
Гипотеза, есть такая гипотеза, но даже такой теоремы нет.
Не, ну просто Habira не стал доказывать, а Гусаров посчитал, что очевидно.
Нет, это, мне кажется, никто не может ее доказать на самом деле.
Ну ладно, не может, значит тогда я ошибаюсь, хорошо.
Okay, so for string links, what do we have for string links? In this direction there is a theorem also this is just Habira, Gusarov didn't prove this. And in this direction it's a conjecture. That both of them write this conjecture for string links. So they couldn't prove it. But now if we allow n equivalence, we compare it with CR equivalence. So like we had before, for each n there exists an R. Actually, R is a function of n and the number of components.
Сергей Александрович, простите, я пропустил, почему там вопросительный знак? Почему ровно так же не...
Гипотеза.
Нет, простите, я тут перепутал другую сторону. Like this.
Ну да, в другую сторону. Нижняя стрелка всегда хромает, а верхняя, она очевидна.
Yes, the upper arrow is this theorem. It is for links and string links.
Да.
It is easy. It is what we discussed before, essentially. But in the opposite direction, it is difficult. For nodes, it works. For string links, it is conjectured to work, but nobody was able to prove this. Yeah, but okay, there is a theorem that this holds rationally. This is a theorem of Matsuyo. Piotr Mikhailovich, is it correct way to pronounce this French name? Monsieur. So what means rationally? Rationally means first that we consider finite type invariance with values in a vector space over the field of rationals, rational finite type invariance. And also, so what does this arrow say? If two string links are not separated by type n invariance, then they are related by Cn+1 moves. So actually no. So if they are not separated by rational type n invariance, then if we take sufficiently many copies of this string link, connected sum of sufficiently many copies of the same string link, then they will be related by Cn+1 moves. So rationally in both rationally n equivalent and rationally Cn+1.
Ну еще год поставьте. Массив, когда доказал?
Массив 2009.
Ясно.
And here we also have, so for links there is no theorem, conjecture only. And for string links there is a theorem again by this Monsieur. Same here. And this is actually what I need. So Habira in his paper tried to prove a weaker result. So he tried to prove that Habira tried to prove that n equivalence for all n implies Cn equivalence for all n. But and it was before, it was 2001 maybe. But I found a mistake in his proof. I don't know if Monsieur found, probably he also found, he has a correct proof, I hope. But I like Habira's proof better, so instead of using Monsieur proof, I will correct Habira's proof. So Habira proves it in this language. And Monsieur proves it in the language of three manifolds. Instead of moves on links, he has moves on three manifolds. And I don't like it because I want PL isotopia and it will be difficult to do it with three manifolds. Maybe it's possible, but...
Sergey, actually I don't see from the pictures of C1, C2, C3 how C4 and the higher Cn were.
Well, so this is a picture of C3 move. If you erase this V, this is a picture of C3 move. To obtain a C4 move, you select one of these four strands and replace this strand by this picture. Both in the beginning and in the end. You replace the same strand by this picture. It's called big doubling.
So any of the strands. Any of the strands.
Yes, one of them. You select any one of them and replace it by this picture. So you will obtain several moves from each C3 move. You will obtain several C4 moves. Okay?
Okay, this was one question. The other was, I had actually difficulties to see why the C2 move is equivalent to this triangle move. Because simply C2 had 4 crossings, the triangle had only 3 crossings, and
Well, it takes some effort to see this, but I think if you draw it, you will see.
okay.
It's not completely obvious, but it's easy.
Okay, you tell it, I accept it at the moment.
Uh-huh. Let me explain what was the problem in Hagira's proof of this theorem. Yes, maybe before that I answer Misha's question why everything works for knots but doesn't work for links. The answer is the following. So there is so let L be the monoid of string links. So under the obvious connected sum, you just draw the two cubes. Here you have one string link and here another, and you just take the connected sum. Then you can consider the quotient L modulo CK. So this is CK equivalence, and you can consider it as a subset of L cross L.
Ну что сейчас доказываете? Рациональную теорию?
I answer Misha's question why everything works for knots but not for links. What is the problem with links? So first we have the monoid of string links. And now we take the quotient of this monoid by CK equivalence. And CK equivalence is an equivalence relation, like a relation that lies in this product. And then, if you have, and that is a submonoid, as you can check. If you have CK equivalent links and you add something to them, you will still get CK equivalent links and so on. So then this will be, when you have a submonoid in such a product, it's possible to consider the quotient monoid. It is well defined. But it turns out that this quotient monoid is not just a monoid. It is a group. So for every string link, there exists an inverse up to CK equivalence for each k. So for each k it's a different.
Ну, хорошо.
This was proved also by Gusarov and by maybe only by Gusarov. So somehow it is called Gusarov's group. Maybe Hagida also proved this independently.
Не, ну, зависит от количества этих самых струн. Если струн очень много, а К маленькая, то, наверное, не группа.
Нет, всегда группа. Это теорема Гусарова и Хагида.
Но как же, если К равно 2, а струн там 18, то как же это группа? Потому что он там может это самое по очереди делать. Ну ладно.
Well, I think this group is closely related to the lower central series of the commutator subgroup of the pure braid group. So you consider pure braids, then their commutator subgroup, and then the lower central series. No. I think I'm confused something. But something like that.
А самоновой это гораздо хуже, чем группа. Группа это лучше.
Конечно, да. So this is group, but this is not just a group. It is also important.
В каком смысле? коммутатор есть. Не патентная группа, нужно какой-то...
In the usual sense, lower central series stops at some finite moment. But for nodes, this group is not just nilpotent, it is abelian. And this is clear why. Because for nodes, you can, if you draw two nodes, you can make the second node small and move it here until it gets here, then make it big again. So nodes commute. But there is no such construction for string links. So, because this group is abelian for nodes, you can consider this quotient map. And this group is abelian for nodes. Maybe I should write K because these are nodes. And this will be the universal type K invariant of nodes. Because it is an invariant with values in an abelian group, and it is a type K invariant because of this theorem. If two nodes are related by a CK move, then they have the same invariance of type K. Because there is a converse arrow, this will be the universal type K invariant. And this simplifies everything. So for links, you cannot have such a universal invariant because this group is, well, it is nilpotent, but it is not abelian. And we want finite type invariants to have values in abelian groups. So this is the reason why nodes are much easier than links in this theory. So now let me explain what was the error in Habira's paper. So Habira wrote, so he considered this group, let's call it, no, this is GK. Just string links up to CK equivalence. It is an nilpotent group, and he considered its group ring and the augmentation ideal in this group ring. So this is the kernel of the augmentation map from this group ring to Z, which sends the group to 1, and you can extend it linearly. Okay? So we have the augmentation map. It is defined by sending every element of the group to 1. This group is this quotient. The group of string links modulo CK equivalence. And we look at its group ring, and we look at the augmentation ideal. Okay, the kernel of this map. So this has a different description. No. How about justice? And Habira said the following, that because GK is nilpotent, he said that the intersection of the powers of this augmentation ideal is 1. But this is false. And the example, well, I don't know exactly for GK, but if you take the augmentation ideal in the group ring of Z modulo PQ, where PQ are relatively prime.
Relative это взаимно.
Maybe just to be sure, different primes. This will be okay, definitely. Different primes. Maybe relatively prime is also good. I forgot. And then this intersection, for example, Z modulo 6. This intersection is non-zero.
А что такое дельта в степени n?
The power of the augmentation ideal. Like any ideal, if you have two ideals, I and j, you can multiply them. This product consists of all products x, y, where x belongs to I, y belongs to j. Maybe it's better to say that it is generated by all such products. So you can take any power of any ideal. And
Но какое отношение имеет умножение идеалов к свойству нильпотентности? Там же, когда нильпотентность, там очень специальное умножение, коммутаторное какое-то. Ну, в общем,
well, the relation is that if you the relation is the following. So let us consider this augmentation ideal and subtract 1. This will be a subset of the group ring. So G now is just an arbitrary group, just a subset. But we can intersect this subset with G, because the augmentation sends this subset to maybe plus 1, sorry, plus 1. The augmentation sends delta to 0, but delta plus 1 goes to 1. And the group goes to 1. So it makes sense to intersect them. And this is called the dimension subgroup of G. So it is a subgroup of G, a normal subgroup of G. And the lower central term, dense lower central term, always lies in delta n. This is the connection with nilpotence. For the reverse inclusion, okay, Petr Mikhailovich, so this is a dimension subgroup. So,
подождите, вы там сделали утверждение гамма G, гамма NG.
yes.
Что такое гамма NG?
This is the lower central term. Gamma 1 G is G, and gamma n plus 1 G is the commutator subgroup of gamma n, G and G.
Ну, это подгруппа в G, гамма NG. А дельта NG вообще пересеченная с G.
Yes, we shift the augmentation ideal so that the augmentation map sends it to 1 and then intersect it with G.
Ну, вообще аugментационное отдел лежит в групповом кольце. Но там бывают элементы из G. И если вы еще его сдвинете, то могут попасться элементы из G. Нет, ну, наверное, могут. Я уже это не понимаю. Это там какая-то сложность.
Это очень просто, если это, значит, гораздо проще, чем то, что будет дальше.
Ну, может, тогда дальше и не стоит, если это уже так просто.
So, the augmentation map sends delta to 0 by definition, because delta is a kernel.
Да.
When you shift it, when you add 1, then it will send it to 1.
Ну,
And the group also goes to 1.
почему группу? Потому что так
Also by
устроено.
definition of the augmentation map.
Ну ладно.
So it makes sense to intersect.
Ну, makes sense.
And this is a subgroup of G, a normal subgroup of G.
Да.
It can be proved. This is called the dimension subgroup. That's
Ну,
dimension
гамма
subgroup.
n, наверное, лежит в дельта n, потому что если я возьму такой коммутатор, гамма n,
Yes,
гамма
you
g,
can
то там
try.
я могу его, наверное, увидеть в дельта n как-то.
Yes.
Он там, наверное, просто там любой такой коммутатор, есть специальный вид, единицы непонятно откуда происходит. Ну ладно.
Maybe it's something like you can take the ring commutator G, H minus G inverse, H inverse.
Ну, у вас там вообще круговое кольцо Абелева. У вас там, может, вы на этом примере
No,
расскажете?
it's not abelian.
Z по PZ как не абелиан? Z по PZ.
Okay, this one is abelian.
Может быть, на этом примере расскажете, если он есть контрпример, то, может, не нужно знать всю эту технику.
If it is abelian, it is not interesting because there is no. This will be trivial.
Нет, а вы, ну так вы же утверждаете, что здесь была ошибка.
Yes, this is not true. If you consider Z of Z, this is Laurent polynomial.
Да, понятно.
This is something easy.
Да.
You can also consider the augmentation ideal and the intersection of the powers will be zero, but every power itself will be non-zero. We can understand this. What is this augmentation ideal? It is the ideal generated by t minus 1. Its power is just t minus 1 to the power n. So it is generated by products like t minus 1, I think just t minus 1, and so we raise it to t squared minus 2t plus 1. Yes, so no matter which power you take, it will be a non-zero polynomial. So this, all these powers are non-zero.
А нет ли у вас под рукой примера элемента из пересечения всех степеней дельта для группы там z по 6?
This example is a little bit, it's not so easy, it takes some effort. But you can consider it as an exercise. Or I can send you a link, a paper. It's about half page of...
Нет, ну, честно говоря, это нужно знать, но просто как-то в конце доклада вы это все сейчас хотите объяснить, я лично не пойму. Ну, конечно, можете попробовать, но мне уже это самое скоро как бы надоест. Может, в следующий раз продолжите через некоторое
The
время.
next time is shape and stop.
Нет, ну, значит, после Щепина. Ну, просто как-то вы сейчас уже перегружаете. Может, вы расскажете до конца доказательства, чтобы мы дослушали, а то уже вообще ничего.
Но доказательство будет использовать это.
Не, ну ладно, вы сделали утверждение, что ну вы сказали, что...
Я наконец дошел до места, которое я буду использовать. Но точнее еще не дошел.
Ну ладно, ладно.
So, the lower central term and lower central term is always included in the dimension term. But the reverse inclusion was an open problem in group theory for 30 years. It was, so there is no inclusion. It was proved by Ritz in 1972.
Это любимый математик этого самого
Mikhailov.
Михайлова.
Yes, and this is the reason why he is the favorite guy of Mikhailov, because Mikhailov likes this theory very much. Indeed, this was many people tried to construct an example, and for 30 years they could not. So it's difficult example. Mikhailov constructed also many examples of this type, more complicated. So he has Rips proved that gamma 4 is not included, delta 4 is not included in gamma 4. For 1 to 3 it's always included, but for 4 it's not included. And Mikhailov has an example that delta gamma 5 is 0, 1, but delta 6 is non-zero, not equal to 1. So even the next one can be non-trivial. But also there is, yes, so maybe I should now state the lemma which I will use. Question?
А у них группы конечные?
Any groups. In this example, the groups are finitely generated, but not finite. Not finite. So the theorem which I will need is the following, or lemma. So actually it is proved by this Monsieur. But I also found an algebraic paper by Hartley from something like 1980. Monsieur is 2009. And this also applies the lemma. So it was done in algebra before Monsieur. And the lemma says that if G is a finitely generated nilpotent group, so in other words, some gamma n equals 1. Then there exists a k such that delta k equals 1.
Ну, так он все и это самое, все и починил.
Yes, this k can be different from this n, and this is why.
И даже теорема Михайлова from n плюс 1 тоже не годится.
Yes.
Но больше так что можно.
Yes, so Mikhailov's example shows that really it can be different from n. Yes. And this is the reason why for links we have to change n by some other number. It comes from this level. And in the case of Habira, he looked just at the infinite intersection. And this is why he obtained a weaker result. For all n is an equivalent, is the same as for all n Cn plus 1 equivalent. But it was a mistake, because if you consider just Laurent polynomials, yes, okay, the mistake is because of this z modulo 6. But if you want to claim that some of these powers is non-zero, then it is not non-true even for Laurent polynomials.
Нет, может он имел в виду какие-то дополнительные свойства нипотентности.
This is what he wrote. He wrote because it is
ZPQ у вас не нипотентна же, хотя она Абелева.
Yes.
Ну ладно, ну похоже, что формально ошибся, да.
So, yes, so it is important to take this intersection. Not just look at the powers, because the powers of this ideal can be non-zero for every n, even this z is an nilpotent group, finitely generated nilpotent group. And the powers of the ideal can be non-zero for all n. But this intersection, delta, it will be 1, starting from some number. Okay, now we can prove something using this lemma.
А вот маленький вопрос не в тему. Вот если только там, если 40 лет была открыта проблема, лежит ли одно в другом, то получается практически всегда лежит. Если да, то известна ли причина?
Well, there are some theorems of this sort, that if G is a nilpotent group, then delta n is always torsion, or you can consider the quotient of delta n by gamma n. Yes, this quotient is always torsion. And moreover, there is an explicit estimate on how big this torsion can be, using some factorials. And this gives us some estimate about how big this number r can be. But if you remove finitely generated, then this is an unsolved question. So if G is a nilpotent group, is it true that some dimension subgroup equals 1? This is an unsolved problem. In the book of Mikhailov and Passy, it is written as an open problem still. It is a recent book, so it's open for 40 years maybe.
Но если она механически порождена, то там могут быть контрпримеры на уровне логических каких-то этих аксиом, так что непонятно, что там рассказывать.
But there are many results. Many results. So I want to tell you a new proof of Montesquieu's theorem. So theorem for all n, there exists an R, which is a function of n and the number of components, and such that if the two string links L and L prime are n equivalent, so they have the same finite, they have the same type n environments. Then they are CR equivalent. So related by CR moves.
Сейчас, чем больше R, тем сложнее написать, доказать, что R эквивалентно, да? Если R, нет, тем проще доказать, что R эквивалентно.
Да, R больше, R будет больше, чем R.
Значит, чем больше я возьму R, тем проще будет теорема.
Ну да.
Если n эквивалентные, то они, казалось бы, нет, потому что CR-эквивалентность это какое-то очень слабое понятие, и редко когда бывает CR-эквивалентность.
Да, пожалуй, там, я все время путаюсь.
Вот если наоборот, n было бы большое, а r бы маленькое, то тогда было бы более правдоподобное.
Да, видимо, так и есть. Сейчас. Yes, I should exchange. R and N. Yes. Okay.
Ну, вроде да.
So we have this group GK, and we have the group ring ZGK, and it is the same as, so we can also look at the monoid ring. So L is a monoid of all string links, and there is a monoid ring. In the monoid there is no division, but also in the ring we don't need a division. So it works. There is such a thing as a monoid ring. So this is the quotient by some ideal JK, where JK is the ideal generated by all differences L minus L prime, where L is CK equivalent to L prime. So this isomorphism is more or less obvious. This was the quotient by CK equivalence GK, and we take the quotient by CK equivalence K. Yes.
Ну так это вот то, что вам не доставало, да, вот эта теорема. Вы там сказали, что вы что-то доказываете.
So, well, I have to prove this theorem, and then using this proof, I will prove theorem 3, but maybe not today, because we don't have so much
Разве
time.
это не есть теорема 3 в каком-то смысле?
No.
В чем она отличается от теоремы 3?
Theorem 3.
Там еще по модулю этих самых, по модулю этих каких-то других еще.
Theorem 3 is about locally additive invariants. So, unfortunately, I cannot understand locally additive invariants without using CN equivalence. So also we have another ideal JK, which corresponds to Vassiliev invariance. So it is generated by all singular links. So for a singular link, so we have this formula V of L equals V of L plus minus V of L minus. So L has a double point, and L plus and L minus are like this. Yes, resolution. If you have several double points, and you apply this formula to each double point, then you obtain a sum. So L equals the sum over, so L has n double points. So this is the sum over signs epsilon 1 and so on epsilon n plus or minus 1. And I take the product of these signs, and then V of L epsilon 1, epsilon n, where this is the resolution of all double points according to the cells.
Мы знаем это определение.
Okay, so the ideal JK will be generated by all such sums. Let me call it sigma. So and I put sigma here.
А где он это делал? В групповом кольце группы G, что ли?
Sigma L. So sigma L, where L is a singular link. Yes, it lies in the group ring in the group monoid, in the ring, in the monoid ring. L is monoid of string links, and this is the monoid ring. So it is generated by all such sums, sigma L, where L is singular link with n double points. So then JK, well first I should say that what is a type n invariant? Type n invariant is a homomorphism from this group ring to some abelian group such that this JK lies in the kernel of phi. A type n invariant is a homomorphism which vanishes on this ideal, because it has to, or on so JK plus 1, sorry, it has to vanish on all singular links with n plus 1 double points, n plus 1. Yes, and a singular link with n plus 1 double points is essentially such a sum of non-singular links, alternating sum of non-singular links. And this is what we are saying here. This ideal is generated by such sums. So we, of course, a type n invariant is a map from L to abelian group, but we can extend this map linearly to this monoid ring, and then it will have to vanish on this ideal. Okay, now there is the inclusion. JK lies in IK. And this is easy. This is the pictures which we did about C2 moves, C3 moves.
IK, что такое? Нет, не написано.
Yes.
Это Хабиры, что ли?
Okay, how about this? Let us
написано.
Let us call this Viki. I'm always confused. Let us call this Viki. Vasiliev. Vasiliev. And this will be called WK. Right? So WK lies in Viki. This is easy, and this is because type K invariants are invariant under CK plus 1 move. Only I'm worried about n plus 1 here. So see, where is n plus 1?
Не, ну с точностью до правильных обозначений.
Okay. This should be n plus 1. N here, but n plus 1 here. Then everything will be correct. Okay?
Ну, наверное.
But there is no such inclusion. Or at least I don't know if such inclusion exists. And this is the problem. Instead of this, There is another inclusion.
Вот в теореме Моисеева надо, значит, использовать, что там ослабленное вложение.
There is another inclusion. V q times n plus 1 lies in W n plus delta q. So we have this augmentation ideal. So this is the main geometric theorem of Kabira's paper, I think. Actually, there are some versions of it, but this is a corollary, let's say, of the main geometric theorem. So essentially, so you see what is this V, this ideal V. It consists of many such pictures. Essentially, this is a C1 move. Yes, this is a C1 move. But we have many simultaneous C1 moves. And here we have Cn moves. But he cannot reduce many simultaneous C1 moves just to Cn moves. He also needs this augmentation ideal, and augmentation ideal geometrically means that we need to take product of string links because it's a product. So each of these string links is not very interesting, but there are quite many of them. So what is the augmentation ideal actually? Actually I claim that it is the same as V1 and also the same as W1. Let us understand this. So what is W1, for example? It is generated by formal differences of links which are C1 equivalent to each other. So actually any two links are C1 equivalent to each other. And so we get the augmentation ideal. And what is V1? Well, V1 is generated by such differences of L plus and L minus for any singular link. But if you have any two links, L and L prime, we can connect them by a homotopy. In this homotopy there are finitely many of double points, and each of them there is a link before it and a link after it. And we have this jump. So this difference equals the sum of such jumps, and each jump lies in V1. So delta equals V1. So we have this formula, and I think it's time to start the proof of this theorem.
Лемма еще будет или не будет?
Вот это вот будет использовано, да, вот сейчас она как раз пригодится.
Доказательства леммы не было.
Вот этой леммы нет, она... This lemma is relatively easy to prove for finite groups, and maybe just one page or so. And from this lemma for finite groups, it is possible to show that the intersection of all delta k is trivial, of all finite delta k. But to show this lemma is more complicated, so this lemma is non-trivial actually.
Она как-то странно затесалась между вот рассуждениями про это и то, что было в предыдущем на той доске. Она не имела никакого отношения к тому, что вокруг нее было сказано.
К чему?
Ну вот, по обе стороны от нее вы говорили о, ну вот о дельте вот этой.
Ну, смотрите, вот дельта уже появилась. Вот видно, откуда берется дельта. Она берется вот из этой вот основной геометрической теоремы Хабира. So this theorem is the reason why we have the augmentation, the powers of augmentation ideal. So it is maybe already not so surprising that we will apply this level. All right, so we have our monoid ring, and we have the group ring of GK. So GK was the quotient of L by CK equivalence. Here we also have the augmentation ideal. Let me call it gamma. And here we have delta. And delta goes to gamma because this arrow commutes with the augmentation map. This triangle commutes. So this delta is the kernel of this, and the gamma is the kernel of this. And so delta goes to gamma. Okay, now the kernel of this map, let me call it P. The kernel of P is WN, WK. This was here. So then we have that P of some power of the augmentation ideal plus WN lies in the same power of this augmentation ideal. So because delta goes to gamma, delta to the power L goes to gamma to the power L. And this just lies in the kernel of P. Okay, I should write K. Maybe I write here. Yeah.
So N с L как связаны?
Никак не связано. No connection between N and L.
Для любого L и N?
Yes.
Тогда вообще WN, N вообще лишнее тогда, если нет связи. В формуле в левой части есть N, а в правой нету. Зачем он тогда в левой части, если для любого N нет связи?
Well, this P, I can call it Pn if you want. So we have N here.
Ну, ладно, но все равно, значит, какое-то сложное утверждение для N равно единице, что сложное, а потом все проще. L-то не меняется. Ну я просто правильно понимаю, или
So how about this? Delta L goes to gamma L, because delta goes to
да,
gamma.
это правильно.
Also, Wn goes to 0, because this is the kernel of this map. So, delta L plus un goes to gamma L.
Ну хорошо, ладно. Ну, может так писать.
The reason I write this because this is what we have here
Я
in Habermas.
бы написал дельта L плюс W идет гамма L. И уже этим все рассказал. Зачем там индекс L приписывать, непонятно. Но раз так вам нравится, ошибки нет.
This is the power. I raise this ideal to
Нет,
the
это
power.
нужно, power, но W я могу написать W просто, и это будет, этим будет все сказано, потому что WM лежит в W, и если я для W докажу, то...
No. This map depends on n. I cannot put 1 here. This is the quotient map, quotient by Cn equivalence.
Понятно, для каждого n, хорошо, ладно.
This is the kernel of this quotient map. Okay, so we have this.
А вот из вот ЦК эквивалентности для какого-то К следует ЦК эквивалентности для больших или для меньших? То есть для меньших, видимо, следует?
Да, для меньших следует, да. Yes, CK equivalence or CK plus 1 equivalence implies CK equivalence. This is true. Not completely obvious, but it is true. Okay. So also now we can finally use this lemma. And it tells us that, so what was delta K? Delta K was the intersection of G with delta to the power K plus 1. I can write it differently. Delta K minus 1 equals G minus 1 intersected with delta to the power K. And this also equals, well, I think 0, because delta K equals 1. Yes, so there exists a K. This finitely generated nilpotent group is GK. Indeed, it is finitely generated and nilpotent, Haber approaches. I apply this lemma to this group, and I obtain that there exists a K such that delta K equals 1, and then this intersection equals 0. Alright, so now this intersection, yes, I have a map. This intersection, it lives in ZGK. And I have a map from Z lambda, ZH, sorry, the monoid ring. And here I can write L minus 1, certainly it will go to G minus 1. Intersected with, sorry, this should be gamma, because here I called it gamma. It's the augmentation ideal, but of a different ring. Both of them are augmentation ideals. I'm applying this lemma to this group GK, and its augmentation ideal is called gamma. So I have to write gamma here. And here I will have
То есть дельта тоже является степенью чего-то само по себе.
yes, delta itself is not a power, but we can...
Не дельта. Вот маленькая дельта.
Little delta is this intersection. In our case, this should be called gamma. So here I'm writing this delta to the power L plus W no, to the power k plus Wn. Because this goes to gamma to the power L, so this goes here and this goes here. This intersection goes to this intersection. So I just wrote this sum there in the bottom. It goes to gamma to the power L. Delta to the power L plus Wn goes to gamma to the power L. Here I just changed L to k and wrote this sum. It goes to gamma to the power k. Okay? And this goes to this Gn. So, but this intersection is 0. So this intersection must lie in the kernel of this map. And the kernel of P is, we know, this is Wn. Yes. And now we use Habira's theorem. This thing is what we have here. So we have a chain of inclusions. V Q times n minus 1. Okay, L minus 1 intersected with this. Lies in L minus 1 intersected with this. Wn plus delta Q. And now this one lies in Wn. So this is almost what we wanted. This is Vasilyev ideal and this is the Habira ideal. And we almost get that the Vasilyev ideal of some bigger index lies in the Habira ideal, except that we have L minus 1 here. This is not the augmentation ideal, it is exactly the set consisting of such differences, link minus 1. And we have, so what do we want to show in this theorem? If two string links are equivalent, so R I think will be this Q times n minus 1, and Q comes, Q is this K, because we need this K. K comes from the lemma, and then Q can be set equal to K. I can write K here. Yes, so this is our number R. K times n minus 1. But K is a complicated number. K comes from group theory, from this lambda. So we want to prove that if two string links L and L prime are equivalent, then they are CN equivalent. Well, if their difference lives here, then they will be CN equivalent, because this was the definition of WK. And we know that their difference lives here. So we almost prove this, because this difference doesn't live here. This is a little problem. But this problem can be solved because this V and this W are ideals. we can these are two-sided ideals. We can multiply on the left and on the right. And this GK is a group, so every string link has an inverse up to CK equivalence. So we can multiply on the left by the inverse, and then we get 1 instead of this one. And then we do some other multiplication and it cancels and everything works. I can tell this in more detail, but maybe it's not necessary. Do you want to hear more details how I do this? No?
Ну, может, Миша захочет. Я не хочу.
Нет, Миша говорит, что не хочет.
Я тоже не хочу. Я хочу эту самую.
So
Мне уже...
This is the technical
Мне
part.
скоро такси не сегодня. Давайте.
So
Скажите что-нибудь такое.
Monsieur's theorem is proved. And, okay?
Наверное, да.
Any questions about Monsieur's theorem? No? So next, it would be time to prove theorem 3 by using this argument and some additional.
Next time.
Yes, but the time is, what is the time?
9 часов.
9 o'clock, so it's
4 часа работы.
unfortunately time to finish.
Нет, ну просто можно и сейчас, но я уже не запомню. Но если Миша запомнил, тогда
yes,
он может
so
сейчас.
maybe.
Просто я как-то уже это самое...
Misha, do you want to continue?
Если в ближайшие недели возможности продолжить не будет, то, наверное, имеет смысл сейчас.
Ну ладно, тогда вы продолжайте, я пойду уже.
Ладно, до свидания.
До свидания.
Andreas, how about you? Do you want me to continue or it's better to stop? Next
For
time.
today, I must say I'm tired and cannot really concentrate.
Well, okay, then maybe I should stop. But next time I cannot continue because Shepin will give a talk. But maybe some other day I can prove it. Or I can tell the proof to Misha and it will be recorded. That's another option. Misha, did you want to discuss some questions today?
No.
Okay, then I think it's better to stop. So otherwise we cannot discuss your questions.
Вот у меня еще по этой лекции пару вопросов встает. Первый вопрос. Возможно ли коротко объяснить, из каких соображений можно было придумать именно такие вот эти вот циклодвижения, чтобы вот соединимость через них была равносильна неразличимости через инвариант?
Actually, I didn't say that there are many different definitions of CK moves. I told you just one definition of CK moves, and there are many other definitions. This definition is from Habira's master thesis, magisterская диссертация. And then he used another definition connected. So for example, C2 move, which was a delta move, can also be described as a connected sum with the Bromian rings. So you take in your link, you take 3 strands, and you take connected sum with the Bromian rings. When you not draw the Bromian rings, this is another equivalent description of the C2 move.
То есть когда делаем, то есть вот эти вот 3 внешние дужки, они там пересекаются дальше. Это вот все внутри той картинки.
Yes, so there is some link.
Сейчас.
This is some picture.
Вот само движение в чем состоит?
The move is that we, so there was nothing here before, and after we add this connected sum. Okay? And for C4 moves or C3 moves and so on, you can also represent it in this way. So you can draw some Brownian link corresponding to a tree and take such a connected sum. And there are other also pictures of this CK move, so there are many ways to define them. I think one way how this can be understood is the following. Type K invariants are also related to K, I think K point configuration spaces. So if you, for example, if we return to this C2 move, and we put I think yes, we put two points. We put just 2 points on the components of the link. No matter where you put 2 points, these 2 points will not notice this move, because you need a third point to so there must be 3 points going along these 3 strands, and if there are just 2 points, then you don't see anything about the third strand. If you look at the configuration space and you try to consider some equivariant homotopia, so every link gives some map on K point configuration spaces. Actually, it's an embedding, but maybe it doesn't matter. It's a map in particular, and then isotopy gives rise to equivariant homotopia, actually isovariant homotopia. But then, if you have a fixed K and you look at K point configuration space, then you can make some tricks. So you can do a CK move instead of an isotopia, but the CK point configuration space will think that it is an isotopia. So this is another way to look at type K invariants, and there are some theorems which say that this is actually so. And from this viewpoint, I think CK moves are quite natural, because you can see that they are not. This is something that K point configuration spaces do not detect, but K+1 point configuration spaces do detect. Maybe there is more what can be said here, but it's a long story.
Еще был вопрос, сначала предварительно, не помните ли вы, случайная диаграмма узла дает простой узел или составной с вероятностью 1? Что-то из этого я не помню.
No, I don't remember, sorry.
Ладно, это тогда позже посмотрю. Там с этим еще вопрос есть. Ну, в принципе, могу прямо сейчас, это, наверное, не очень долго.
But is it related to this?
Да, это связано не с самой темой, но с одним фактом, который вы упоминали.
Andreas, do you have any questions?
Not at the moment.
No?
Not at the moment.
Okay,
Not
okay,
at the
okay.
moment.
Okay, Misha has one more question. Regarding your previous question, I can add something. So there are many ways of coming to CK moves. So, for example, Gusarov had a different approach. He considered surgery. Actually, Habir in his paper also starts from surgery. So it's a certain surgery on S3, whose result is still S3. So you can start by thinking about which surgeries change the link, but don't change the 3 sphere. And this can somehow this leads to the CK moves, and I also wanted to say some other motivation, but I forgot.
Я почему-то думал, что случайный узел составной, а он где-то простой.
Well, I think these random nodes are, you can choose a different, you can always choose a different probability measure, and then the answer will be different. So it's
Тут прям можно придумать, чтобы разные ответы были. То есть, мне
I
кажется,
think for all such questions in topology, it very much depends on the choice of the measure. Some other person will choose a different measure and will obtain the opposite answer. So
я когда пытался очень много способов там примерно под эти узлы придумать, и для всех из них, было ощущение, что они все там отличаются на асимптотически ничтожные перестановки.
well, this, there are infinitely many nodes, but countable many, and different types. I mean, you can think of very many ways to introduce a measure to this space. So somehow.
Ну вот я знаю, значит, длину формального определения, число пересечений, дальше еще можно там, допустим, минимальную кривизну, при которой она реализуется внутри единичного шара, что-нибудь такое.
Yes, but I don't see why this makes sense. Why this has to be used. These measures are better than some other measures.
Нет, это просто то, что, то есть вроде не так много в принципе можно придумать способов.
I think very many, but
А вы можете назвать что-нибудь еще принципиально другое?
This just doesn't sound interesting to me.
Просто как раз мне кажется, что тут совсем от способа не зависит, что все способы, которые можно придумать, дают одинаковые результаты в подобных вопросах. Там, допустим, почти все узлы альтернированные или нет, простые или нет. Вот.
I don't believe it, but maybe it's a question. It's really a question of faith, and it's not not something falsifiable. So there is one thing which I can add here about colored type n invariance. So actually there is such a thing as self-CK move, which is quite popular. There are many papers in Japan about self-CK moves. So self-CK move is a move which involves strength only from one component. And similarly to these pictures which we had, you can show that if you have a type n and so on, n invariant, then it doesn't change under self Cn plus 1 moves. Is invariant under self Cn plus 1 moves. Okay? It's more or less the same argument. Because here you consider n plus 1 tuple points on the same component only. And here are moves which involve only strengths from the same component. But I think nobody proved anything in the opposite direction. So this is completely open, but it must be more complicated. So because we have this Kirk-Livingston problem or conjecture, Kirk-Livingston conjecture, they say that for n equals 2, there are infinitely many such linearly independent invariants. And well, but actually from the viewpoint of CK moves, it's more or less clear why. If you allow only self-CK moves, well, this CK moves, they are related. So Habira draws pictures like this. He actually draws a unit trivalent graph with leaves, and then you make a surgery along this graph, and this will be a CK move. This graph determines a CK move. I think it has some framing, but there are some details here. And then he proves some lemmas, like you can actually move such graphs by homotopy and even intersect these edges with the link. And the way he proves this is, of course, because he looks at all CN moves, including moves that involve strands from different components. So an intersection between such an edge and a component, he reduces it to several intersections or several CK moves involving different components. But if you have CK moves involving only one component, then it's probably impossible to prove such theorems. And then you will have these graphs will be sort of in the complement of the link, and they are not allowed to intersect the link. I mean, maybe they are. So these strands are from the same component now, and okay, these edges are allowed to intersect this component, but they are not allowed to intersect other components. And so you can wind them around other components as many times as you wish. And this is probably why you have the infinitely many such linearly independent environments. So it's maybe it's possible to prove the Kerr-Cleveland conjecture by looking at self-CK moves. So that's it. So let us finish. No more questions. All right, goodbye. Thank you for listening.